Both of them.
Alright.
Wait, I
Okay.
thought you were recording.
It's
I'm
recording
going to
now.
be recording now.
Oh, okay.
Sorry, guys.
It's our first lecture. Please be kind
First
to us.
lecture jitters.
We're working through the kinks here.
Hello, people who are recording, who we just turned on to now. Sorry about that. Here's the first slide. There's a bunch of stuff you need to do.
Okay.
Thank you. Okay. Sorry, guys. Bit scatterbrained today. Okay, this is very important. I need you guys, if you haven't already, our main source of communication is going to be through Discord. So if you haven't yet already, please join the Discord. I have a link here. And also, super important, there's a channel in the Discord called Add Roles. And I want you guys to go to the Add Roles channel, and you're going to react to this message with the ops role, which is the leftmost one. It looks like a little soldering pen. But yeah, if you click on that, you'll get all of the ops channels, which is where all of our messages and announcements and everything will be. So please do that. It's very important that you do that. Don't forget to do that. I'll send out another announcement about it probably, but make sure you do that.
Okay.
This is a non-ops related announcement, but IEEE is having a GB info session, which is stands for General Board. General Boards are really awesome, and I really recommend you come and join a GB. It's really fun. Me and Margot both had a GB last year.
Yeah, it's a great way to. It's a social event, so it's again a really great way to meet other engineers. Did you have a question?
I think unfortunately it overlapped with small works exams.
Oh, really?
I see. Okay, well, we'll figure something out. We'll definitely talk about that with with other people.
Also, it might be recorded.
Yeah, we'll figure something out. No worries. And then the most important thing is just remember to be respectful, responsible, and ready to learn. Ops is about learning, and we have really no expectation of you knowing any electrical engineering knowledge, but just be ready to learn from your peers and also from us and other people as well. Okay. And then...
Okay, so this is our schedule for throughout the year, just sort of like the concepts that we're going to be covering. So this fall, we're going to doing some of the basic stuff. We're going to be going over breadboarding, soldering, and reading schematics. And we're going to have 3 projects. Obviously, we're starting a little bit like halfway through fall, so they're on the quicker side of projects. And not too hard introductory ones, but still will be pretty fun. In winter, we're going to get onto the fun stuff, programming microcontrollers, wired and wireless communication, 3 projects. 2 of them are going to be very fun. Have little competitions there, super fun. And then in spring, we're going to be doing more complex components and designing, building, applying sensors. And also that's where we're going to have our capstone, which is like a wall-following robot. That's sort of like the big thing that we make at the end of it all. And yeah, that's sort of the schedule for the year.
Now, just a couple of things. You guys will be able to look into your ops boxes later, but these are the 4 things that you guys should have. If for some reason you don't, definitely come up to us and we'll rectify that. The Arduino Nano, don't worry about that. We'll talk about that in the
we were going to
winter.
get the Arduino Nano, but the Amazon shipping got delayed, so unfortunately we're going to give it to you guys later. But it's fine, we're not using it this quarter anyways, but unfortunate.
Yeah. And then one other thing, when you guys are in the IEEE lab, there's going to be an ops parts drawer. Your ops box is going to have everything that you need to complete all of the projects, which is why you're going to need to go to these drawers to get them. And I just wanted to give you a photo just so that it can be kind of confusing.
It's like at the wall where the door is. So you walk in, and it's like the wall that you entered from the door, if that makes sense. So like you walk in, and it will be behind you.
Don't worry, we'll definitely show you everything, so no need to memorize all this. And then this is really important. I know there's a lot of information on this slide. Essentially, you guys are going to be split into 3 teams. It's a great way to kind of get to know people in a smaller setting. But the important thing about these teams is that on every single project due date, you're going to be assigned a time slot where you can get checked off for these projects. And it's really important that you come at your team's assigned time because that reduces the amount of people in the lab just for COVID safety reasons. We also have a couple of different other ways for you to get checked off as well, but I just wanted to emphasize coming in at your specified time on the due date of the project checkoff. Sorry, I can move as well.
And you can also, if you Also, you can do Discord. Also, if you can't make it to the lab for whatever reason and you have your finished project, just take like a video of it, shoot it to either of us on Discord, and we'll send you the questions then. That's also another way you can do it. I know I definitely sent more through Discord than actually talking to the leads last year. So no hard feelings if you don't want to come into the lab and see us.
Does anyone have any questions so far? I know we're just bombarding you with a lot of information right now. All good? Okay, cool. And then this is just a quick info about our lab hours. I know it's out of focus right now, but if you go on the slides, it's a better image quality. Basically, ops hours are from 12 to 5 on Wednesdays, so that'll be a perfect time to get to talking to your ops leads. One thing to note is that a majority of the officers on the board know ops, so you can definitely come to them as well. You don't have to just come to me or Preston for ops information.
Yes.
Cool. All right. Now we're done with all the housekeeping stuff. We can finally get into the interesting stuff, which is talking about currents, voltage, and resistance.
Sorry for all the boring stuff. It gets so much more fun from here.
Okay, perfect. So do you want to take that?
You can be current.
Okay, perfect. So, how many of you guys know what current is? Yeah, I'm sure we all know what current is, right? It runs our computers, our phones, and everything. But what's really interesting is that essentially current is just a charged particle moving through a material. And I have here a diagram that's showing you how the electrons are moving. It can be a little bit confusing, the convention, because technically electrons are moving from the negative side to the positive side. As you guys can see in this diagram here, the electrons are jumping from each section to the positive side of the battery. However, general convention in electrical engineering is to say that the current flows from positive to negative. It's a little bit confusing, but if you just remember current flows from positive to negative in terms of our circuit diagrams and everything, then you'll be perfectly fine.
You'll see this referred to, the way current flowing from positive to negative, you'll hear that as conventional flow, whereas electron flow is the other one, which goes from negative to positive.
Mm-hmm.
Basically, Benjamin Franklin discovered it first and was like, oh, current probably goes from positive to negative, and then they found out it didn't, and it was too late to change it. So now we have this unfortunate circumstance.
Yeah.
Also, current is measured in amperes, which is the letter A, and also sometimes is abbreviated with the letter I. So you'll see that later, but yep.
Okay. And stop us at, again, any point if you have any questions whatsoever. And again, this is just another note about how electrons flow as opposed to how the current flows.
And voltage. So voltage is the difference in potential energy which results in the movement of charge. Basically, electrons all repel each other. So a battery has a lot of electrons in one place, and so that has high potential, and they want to go to low potential. So they try to flow from areas of high potential to low potential, which is how electrical circuits work. So in the battery, you have the source of both high and low potential, and then what you do with your circuit is just connect the high and low to make it flow from one end to the other. So if you look on our battery, we have a 3.7 volt terminal, which is the red wire, and we have a black terminal, which we refer to as ground, which is 0 volts. And so it wants to flow from red to black, and that is, in this specific battery, the red is 3.7 volts, which is what we measure it in. We measure it in volts. And black is ground, which is 0 volts. That's the convention.
Yeah.
So any questions about that?
One thing to note also is that general convention is that the red terminal is positive and the black terminal is negative. So the positive is always going to have the higher value, like 3.7 volts, and the black terminal is always going to have 0 volts relative to the red terminal. Now, I know this can be a little bit confusing, especially if this is your first introduction to electrical currents and stuff like that. So it's easy to think of current as water, because water and current oftentimes flow or work in the same way. So you can honestly think of voltage as the difference between this top part of this tube and then the bottom part. Obviously, there's going to be a lot of energy up here that wants to flow down, and so you can think of that as voltage, as just some sort of energy that's stored here that's just waiting to be used eventually. Does that make a little bit more sense? Okay. So again, yeah, the difference in water pressure results in the water flowing from the positive side to the negative side in terms of a battery.
Yeah, so then another sort of term that we have for circuits is going to be closed circuit versus an open circuit. So a closed circuit is the one that we see on your right, this one, the one where the light bulb is on. See, the circuit is connected. The positive and negative terminals are connected. The switch is closed. And so that means that electricity is flowing in a closed circuit. Versus the open circuit where the light bulb is off, if you can see the switch is open, and so electricity can't flow. There's no connection, so it is an open circuit. Electrons not flowing.
Yeah. Perfect. So I have a couple of questions for you guys. Feel free to raise your hand and answer them. The first one is, what would happen to the water if the bottom was plugged up? Like, let's say there was some sort of stopper here that wasn't allowing water to flow. What would happen?
Water would stay.
Exactly, yeah. And so, and in terms of thinking of electronics, what would you say this is equivalent to? An open circuit, exactly. And that's because the water is incapable of flowing. So you can think of an open circuit as current not being able to flow through the circuit. And then you want to...
Yeah, so what would happen if the bottom was connected to another two? Yeah, it wouldn't flow.
And what will we call that in electronics? A closed circuit. Perfect. And what does the water represent in this case?
Electrons.
It represents the flow of electrons. So it represents the current. Perfect.
Okay, and then resistance. So the next thing, we covered voltage and we covered current. This is the next thing, this is resistance. So when we talk about resistance, we resist the flow of electrons, we resist the amount of current through having resistance. So yeah, basically we have a component called a resistor, and this will slow the current down and allow the voltage to drop across it. So the symbol for resistor is this little squiggly thing. Also, you might see it as a box sometimes in like Europe, they do it, but here in America we use the little squiggly thing. And so this is an example of a circuit which has 3 resistors in it, and resistance is measured in ohms. Yeah, so that's the main resistance stuff.
How many of you guys have experience with working with resistors or understand why you need it? Yeah, okay, cool. So it's really important to understand that resistors, although it seems like it's resisting change, you don't want it to drop the voltage or whatever the case may be. They're incredibly important in making sure that our circuits are safe and stable. So they're an incredibly important component that you're going to be working with a lot further down your career. In terms of representing resistors, there's a really easy mnemonic device in order to remember the color coding system. Essentially, we have a bunch of different colors ranging from black to white, and these colors represent basically like a hundredths place or a tenths place or a thousandths place to give you the actual value of the resistor.
Yeah, so this is what a resistor will actually look like when you use it in your circuit. It's just this little, obviously very small, but it's this little tiny thing and it has a bunch of colors on it. So the way you read this is you start at the end that's like not gold. Most resistors have like a gold or silver end. So you start at the opposite end, and then you'll read each color will tell you each digit in the thing. And so this is what this diagram is kind of telling us. The first one is like the very first place on here. So like if we have green here, we're going to have that corresponds to the number 5. And then the next one over would be blue, that corresponds to the number 6. And then the last one before the gold or silver one is going to be referred to like a multiplication factor. So in this case we have orange, which is times 1,000. If we had, and you can read the chart there to see what each of the different multipliers are. And then finally, this last one is what we call the tolerance. And tolerance is like plus or minus a certain value. So gold is plus or minus 5%, silver is plus or minus 10%. It gives like the range of value that this resistor could be, which is kind of confusing, but you don't really have to worry about that too much.
It's
just worry
essentially
about.
just like the standard deviation of the resistance, because generally you're not going to have a perfect 27,000 ohm resistor. You're going to have something a little bit more or a little bit less.
Yeah. Sorry if this is a bit confusing. Also, pro tip, you can just look up like a resistor color code calculator. Where if you have your resistor, you can just type in the colors to it, and it will tell you what resistance it is. So if you're being confused, just do that. It's nice, helpful.
Yeah. Are there any? Yeah. Go ahead.
Why can't you make perfect resistors?
Why can't? Well, I mean, in the real world, it's impossible to make anything perfect. There's always going to be some sort of issue or some sort of, like, for example, a wire. In our circuits, we always imagine them to be perfect wires, so there's no resistance in them. So they never drop voltage across the wire. However, in real life, it's almost impossible to make a perfect wire that has no resistance, because materials themselves have some impurities in them. So although it's impossible to make a perfect resistor, it's like the variation isn't so big that we can't use the values. Does that make sense? Okay, perfect. And yeah, it's really great to get a little bit of practice in terms of reading these color coding schemes. However, we'll teach you another way to definitively figure out the resistance of your resistor in a later lecture. Perfect. So moving on with the water analogy again, you can think of resistance as some sort of tightening of the tube. Essentially, this is going to restrict the amount of current or water flow that can flow through the tube, and that changes the voltage or the amount of water that can flow through. So that's another way to think of resistance if for some reason you don't like the idea of voltage drops.
Okay, LEDs. So now we've gone through the main the main stuff on the circuit. This is like what we're having electricity do, which is light up an LED in this case. So LEDs are lights. They stand for light emitting diodes, and when you put a current through a diode, it causes a voltage drop, and basically it uses that to create light. So important thing about LEDs and about diodes in general is that current can only flow through one direction in a diode, which we have that represented on the little symbol. It's like a play button, a triangle, and a line. So it goes from like through, like if it's an arrow, the current has to go through that way. And also to represent this with a physical LED, we have one lead is longer than the other lead, and like the end is flat. So it's very important when you're making circuits and you use an LED, you're going to want to look at you're going to want to look for the long end of the LED will be the one that the current will flow through the positive side. So like from your battery will go through the positive end and then to ground from the flat end. If that makes sense. Yeah. Any questions about LEDs?
Now, we've gone through a lot of important concepts in terms of electrical engineering with voltage, current, resistors, and LEDs, and now we're going to put it all together. Basically, I have a schematic here of a circuit that will light up an LED, which is pretty cool, because what we're trying to do is control electricity. So essentially, we have a voltage, a resistor, and an LED, and that will cause it to light up. However, essentially for your first project, you're going to have to determine what the correct resistance you need in order to make that LED light up, because it's not going to light up at any resistance value.
Yeah,
Okay.
take this one.
Okay, so a couple of things to note in terms of building a circuit is we use a passive sign convention. Essentially what this means is with passive elements such as a resistor, basically a passive element is an element that doesn't take any power. It actually consumes power. So we say that the current flows from positive to negative for a passive element, and then the opposite is true for an active element. Can any of you guys try and identify what the active element in this circuit is? You don't have to be right. Yeah. Yeah, exactly, the battery, because this is producing power, and so therefore it's an active element. So when we say that the current flows from positive to negative for an active element. And this is all a lot of really important convention that you should follow, especially when learning electrical engineering and learning these really basic topics. Perfect. And can anyone identify another passive element in this circuit? There's only one more, yeah. Yeah, exactly. All right.
Yeah. So in summary, voltage is the difference in potential energy, which allows electrons to flow. Current is the flow of electrons because of this potential difference, and the resistance is what slows the flow of the current.
Are there any other questions or concerns? Do you guys have anything you want to clarify in terms of what we've gone over? Perfect, okay. Now let's put it all together. Now, one of the most important topics that you'll be learning is Ohm's law. And essentially what this does is it creates a relationship between voltage, current, and resistance, which is really amazing because we can use this really simple law in a lot of other circuit analysis. So essentially what this says is that the voltage is proportional to the current times the resistance. And again, you can use this in all types of circuits to be able to analyze them, especially when they get a little bit more complex. And as long as we know 2 out of these 3 variables in this equation, we're able to figure out, for example, if I knew the voltage across a resistor and I knew the resistance value, I could figure out how much current was going through that resistor. I could also figure out the voltage drop or even the resistance value that I need for a specific voltage and current value. Okay, so I have a practice question for you guys. If I have a voltage of 110 volts and a resistance of 2200 ohms, what is the current running through the resistor? What was that? 0.25. 0.25, yeah, exactly. And how did you come up with that? Yeah, exactly. So essentially what you can do is, again, you can just take 110 volts divided by 2200, and that gives you said 0.25? 0.05, perfect. Okay, awesome. Are there any questions here about how we got that?
Okay, so now we're going to go to breadboarding. So in your ops box, when you get it eventually, you're going to have a thing in it called a breadboard, which just looks like a white board with all these little holes in it. And those holes are what we use to connect our electrical components to each other. And the most important thing about a breadboard is that each of these horizontal rows here are electrically connected. So you can imagine like a wire connects each of these to each other. So if you put so if you put 2 things in here, they'll be like connected by a wire across, but not down the rows, only across the breadboard. And so that will be very important. Basically, we want to put like one component from one row to another row to like show it flying from one thing, if that makes sense. And also, but for the edges of it, where we have a positive row and a negative row, these are connected vertically, and generally what you want to use these for is you want to put your voltage of your battery on the red row, where it's like if we're using an Arduino, it will be 5 volts, and then on this side it will be ground, which is 0 volts. And we want electricity to flow from the red through our components and then back into the blue, the ground.
And quick note, breadboarding is just a really great way to prototype a circuit before you solder it or you design it on a PCB, just to make sure that it actually works. So this is a really convenient and simple way to design circuits. And we'll go over more about nodes and what it means when this entire horizontal line is connected through a wire. We'll go over more of that later on. And we'll talk about shorting circuits and stuff like that in the next lecture. And then here are a couple of resources if at any point you're confused about what we went over or you want to learn more about it. And that's pretty much it in terms of lecture. A quick note, our next lecture is going to be next Thursday. So I know a lot of people had availability on Thursdays at 7. So that's going to be when our following lectures are going to be Thursday at 7. Thank you guys so much for coming. If you guys want, we're gonna all, well, you guys need the ops boxes, so we're gonna all head over to the IEEE lab now to pick up your ops boxes and kind of get a quick tour of the IEEE lab as well. But thank you guys for coming to the lecture.
Okay, I need to stop the recording. You stop the camera recording.